Good morning, students. Let us start the analog electronic circuits class now. I'll briefly revise whatever we discussed in yesterday's class. We have been discussing the voltage divider bias circuit here, and we already know that the gate current is 0, so we can easily find out the voltage at the gate by applying the voltage divider rule that is given here as Vg equals R2 into VDD by R1 plus R2. Now applying KVL at the input side, we will get Vg minus Vgs minus Vrs equals 0, or Vgs equals Vg minus Vrs. Now substituting for Vrs, we will get Vgs equals Vg minus IDRs. Now you can see that even in voltage divider bias, Vgs is dependent on ID. At the same time, Vgs is dependent on Vg as well. But Vg can be taken as a constant because of the R1 and R2 value. Rs is also a constant. ID will be a variable quantity. Accordingly, Vgs will be a variable quantity. So naturally, we will not get a vertical straight line as we got in fixed bias. We will get a slant straight line as we got in self bias. But in self bias, we had Vgs equals only minus ID into Rs. That way, we used to substitute ID equals 0 and we used to get Vgs equals 0, where origin was 1 point for the graphical analysis. But in this case, even if we substitute ID equals 0, we will get Vgs equals Vg. That means for the straight line which we get in case of voltage divider bias for the graphical analysis, origin is no more a point on the line. But still, this is an equation for a straight line, but origin is no longer a point. Now, the quantities Vg and Rs are fixed by the network construction. Substituting for this Vgs in Shockley's equation and then simplifying, we get this expression. You can also try out. I tried it out on my own for getting this equation. You can also substitute for Vgs in Shockley's equation and you can bring it to a standard form. When you bring it to a standard form, you will get an expression like this, which is in the form of ax square plus bx plus c, where a into id square, a is rs square into idss by vp, b into id, b is minus 1 here, and c is idss into 1 plus vg square by vp minus 4 vg by vp. If you substitute all these values in the quadratic equation, minus b plus or minus square root of b square minus 4ac divided by 2a, you will get the roots for the quadratic equation. That way also we can find out ID. Apart from that, we can go for our regular graphical analysis of finding out ID. Once we find out ID, we can apply KVL at the output side and we can find out VDS as well. I'll show you that in the next slide. Let us see how to obtain a graphical solution. Since any straight line requires 2 points to be defined, anywhere on the horizontal axis, when we put ID equals 0, we will get Vgs equals Vg minus 0 into Rs is Vgs equals Vg when ID is 0 milliampere. Now this Vg can be easily obtained by substituting the formula R2 into VDD divided by R1 plus R2. That's all. In that expression, all are fixed values, so we will easily get the voltage at the gate with respect to ground. Now for the other point, what we have to do? We substituted ID equals 0 here, we got Vg. Conversely, we can substitute Vgs equals 0. We will make left hand side itself equals 0. And then let us solve for the ID. So, when we put Vgs itself equals 0, Vg minus IDRs, or ID equals Vg by Rs. Now, we got one point where ID equals 0 and we get Vgs equals Vg. One more point when Vgs equals 0 and ID equals Vg by Rs. We know the values of Vg and Rs both. So we can easily plot a straight line having these 2 points. But remember here origin is no longer there in this straight line. So now based on this, we have this transfer curve. Now to the transfer curve, we apply these 2 points. You can see here, when ID equals 0, Vgs equals Vg. The value of Vg we will be knowing. Similarly, when VGS equals 0, we will get ID equals VG by RS. So using this point and this point, let me annotate. Now using this particular point and then this particular point, we will have this straight line now. Now we can extend this straight line this side. When we extend the straight line this side, it is going to cut the transfer curve here. When it is going to cut the transfer curve here, we will get the y and x coordinates of the Q point. That's all. This is a graphical solution. As I told you yesterday, in case of self-bias and in case of voltage divider bias, even in the test or even in the exam, we are going to ask only the graphical solution. We will not be asking you the mathematical solution because the mathematical solution is much more complicated. But you must have become familiar by now about how to plot the transfer curve. If some of you have not yet become familiar about how to plot the transfer curve, you should revise all the previous classes and you should work out all those exercises. You should be able to plot the transfer curve on your own. After plotting the transfer curve, you will have to have the straight line. Then wherever the straight line cuts the transfer curve, that is the Q point. This you will have to work it out on your own. In the test also we will be asking this, and even in the exam also we will be asking this. Now based on this basics of voltage divider bias, let us analyze further by applying KVL to the output side. Next things are quite simple because they are similar to our self-bias itself. So applying KVL at the output side now, VDS equals VDD minus ID into RD plus RS. This equation is already familiar to you because it is the same expression which came in self-bias. So VD equals VDD minus ID RD. The voltage at the drain equals total voltage VDD minus ID RD. And Vs equals ID into Rs. IR1 equals IR2 equals VDD divided by R1 plus R2. This is simply a voltage divider network itself. Increasing the values of Rs results in lower quiescent values of ID and declining values of VGS. Now look at this. Increasing the values of Rs. If at all we increase the values of Rs, what is going to happen? It is going to result in the lower quiescent values of ID and declining values of VGS, because now VGS is dependent on ID. If at all you increase the value of Rs, what is going to happen? Now the source terminal is going to be more and more reverse biased because of the voltage drop across this Rs, and that is going to reduce the current that is flowing from drain to source. And when the drain current is going to reduce, naturally VGS is directly proportional to ID and the values of VGS also will get reduced. But VG remains constant. Yeah?
Sir, VGS is also proportional to R, right? RS.
Yeah, RS is fixed, right?
Okay.
RS value, resistor values are going to be fixed. Okay.
Yes.
That's what. When we design the circuit, we are going to decide R1, R2, RD and RS values. Now, based on our design, we are going to compute the Q point. And if at all we don't get the Q point which is desired by us, we will have to change the resistor values once again. So that way, you can see that if the values of RS is increased, it is going to reduce the drain current, and in effect it is going to reduce the VGS as well. This is where we have to take care. Actually, this point was there even with BJT. If you remember, the self-bias and the voltage divider bias circuits of BJT, there also we use the value of RE, lesser value only. For example, if RE used to be 1 kilo ohms, RC used to be 2.2 kilo ohms. Because if at all the emitter resistance increases, then there will be more voltage drop across this emitter, and that will actually reverse bias the base to emitter junction in case of BJT. Same thing holds good here also. Same thing in the sense, if RS is increased, ID will reduce, VGS will reduce. Okay. But you know that VG is fixed now. VG remains fixed. Even in BJT, VB used to remain fixed. So now you can see when the values of RS are increased, you can see that even ID will get reduced and the Q point will come down. When the value of RS is reduced, ID will increase. Naturally, when this resistance is reduced, the current flowing through this is going to be increased. So ID value is going to be increased and Q point will shift towards the upper side of the transfer curve. And when we increase the value of source resistance, then the drain current is going to be reduced, and then because the drain current is going to be reduced in the y-axis, now the Q point is going to be shifted down. Now we should wisely choose the value of RS. Actually, if at all we have to have a ideal plot, I should write a line somewhere here in this manner, so that Q point is somewhere here. Ideally, the Q point must be in the middle of the transfer curve. Just like in our BJT circuitry, ideally the Q point used to be exactly at the middle of the load line. Because it is at the middle of the load line, we can easily deduce that the transistor is exactly in the middle of the active region. It is exactly half on and half off. But in BJT, we don't use the load line as such, because there is no beta here and we cannot actually use the load line in that sense. We will have to plot the transfer curve. Using the transfer curve, again we can set the Q point. That is the idea here. Anyhow, we have to make use of the transfer curve when we use the graphical analysis. So there is no point in drawing the load line when we have a transfer curve itself. In BJT, the transfer curve was not necessary because we had beta and we had a relationship between IC and IB there. So we used load line there. Here we have not touched upon the load line at all because we have this transfer curve. So ideally, the Q point must be in the middle of the transfer curve. Naturally, in the middle of the transfer curve, when that Q point is there, even if you plot a load line, you will get the Q point in the middle of the load line itself. Okay, there's a question here. Vgs equals Vg minus IDRS. So if RS increases, then ID decreases. So the Vgs value would remain constant. How would it decrease? No, here Vg is constant. Now ID reduces. ID reduces. When ID reduces, Vgs will actually decline because Vgs is directly proportional to ID. In this expression, Vgs is directly proportional to ID, right? Vg is constant, Rs is constant. We are keeping the voltage at the gate constant by means of R1 and R2. Now, okay, I'll give you a real example. I'll annotate and I'll give a real example. Let us say Vg is now 2 volts. Imagine this way. Vg is now 2 volts. And let us say here Vsc is now 1 volt. Let us say Vsc is 1 volt. Now Vsc is 1 volt. Vgsc is going to be 1 volt. Naturally, Vgs is going to be 1 volt. Because the total voltage here is 2 volts, 1 volts across this, 1 volts across this. Please remember, this is not BJT, this is JFET. In BJT, we can have base to emitter voltage maximum 0.7 because it is a PN junction. Whereas in case of JFET, it is a reverse biased PN junction. Between gate and source, there is no diode working in the forward direction. The diode is working in the reverse direction. So voltage can increase more than 1 volt also across gate to source. So now if RS is increased, what will happen here? This 1 volt, let us say it become 0.5 volts. Let us say 1 volts become 0.5 volts. Now what will happen to the VGS? Total voltage is 2 volts. 2 minus 0.5 is 1.5. Okay. Oh, that is your question, right? So that is your question. Yeah, even I am also confused now. Anyway, let me think over. I thought I will give a real life example and then let me justify, but that is not working out. When ID is reduced, even Vs will get reduced and effectively Vgs has to increase, isn't it? Yes, this is a serious point. Anyway, I am unable to think about the answer right now. Let me think it over again, and in the next class, let me give a clear-cut answer. But right now the answer is, as per this expression, wait a minute. We have this, let me go back here. We have this particular expression, Vgs equals Vg minus ID Rs. As per this expression, what we can immediately deduce is, Vg is constant, Rs is constant, Vgs is directly proportional to ID, right? We can always write it as Vgs is directly proportional to ID. We can write it this way. Vgs is, even though ID is having a negative sign, it is in the numerator itself. It is not in the denominator. So we can write it as Vgs is directly proportional to ID. So when Vgs is directly proportional to ID, when ID reduces, Vgs has to reduce as per this particular expression, because Rs is increasing, right? Yeah, that is the point. The point is we have increased Rs. So when we have increased Rs, Vg remains constant. Now IDRS, to some extent ID will reduce, but Rs has increased. So IDRS will increase. So naturally Vgs has to reduce. Okay, that is the point. I don't have to wait till the next class now. This is the answer now. The answer is, again look at this expression. We are increasing Rs, then ID is reducing. But increase in Rs and reduction in ID, that is going to increase the net value. When it is going to increase the net value, Vg remains constant. So naturally Vgs has to reduce. Now let me give a real life example. For example, let me come back to the same point where earlier I used 2 volts and 1 volt and 1 volt. Let us say whether I will be successful now. 2 volts and 1 volt and 1 volt. Now Rs is increased, ID reduces. Rs is increased, ID reduces. Now 1 and this may not be 1. Now Vg remains 1. Now even though ID is reducing, the product of ID into Rs is going to increase, because Rs is in kilo ohms and ID is in milliampere. You may again say that milli and kilo will get cancelled, but the change in Rs will be much larger. So that way this product IDRS is going to increase. Now let us say IDRS is going to increase by 1.5. So now what is going to be here? This is going to be 1 plus 1 is 2, right? This is minus sign, right? Sorry, I did the wrong annotation now. Wait a minute. Somehow I am trying to justify my own answer. Okay. Now let us say Vg is 2 volts. I did the wrong annotation here. Vg is 2 volts and this is 1 volt and this is now 1 volt. 2 minus 1 is 1. Now let us say Vg remains 2 and this is going to become, let us say 1.5. The total product of ID into Rs is going to become 1.5. So now naturally Vgs is going to become 0.5. Okay, this way increase in Rs is going to reduce the value of ID, reduction in ID is going to cause the reduction in Vgs itself. I did not think about ID into Rs, I thought only about ID at that time. Now we will have to think about ID into Rs as a product, and the product of ID into Rs will have an increase. Naturally the LHS is going to reduce. I hope you got this point now. Okay, so change in Rs is more than that in ID, so Vgs would decrease, right? Correct. That's why I've been telling you the product of ID into Rs is going to have an increased value on V. Okay, let me continue now. So that is where we have to choose the value of Rs wisely, in the sense The Q point should not shift towards ohmic region and the Q point should not shift towards cutoff region. As much as possible, the Q point must be at the middle of the saturation region. That is the idea here. Okay. Now let me proceed further. Let us solve an exercise based on this voltage divider bias. Can you solve this to some extent? I want you people to quickly plot the transfer curve. Later on, I'll help you in obtaining the Q point. At least the transfer curve part, you must be able to solve it. Let me admit the students. Okay. Now determine the following for the network: VGSQ, IDQ, VD, VS, VDS and VGD. Once you find ID, you will always be able to find out all other things. This is the circuit diagram. Now find out VG. You already have IDSS equals 8 milliampere, VP equals minus 4 volts. Quickly plot the transfer curve. And can you tell me the transfer curve's 2 points? Already 2 points you will be knowing. In the x-axis and the y-axis you will be knowing the 2 points. That is IDSS and VP itself. IDSS in y-axis, VP in x-axis. Now can you quickly compute the other 2 points by using the same method? For 0.3 VP and 0.5 VP respectively substituting IDSS by 4 and IDSS by 2. Put the answer in the chat box. .5 VP corresponds to IDSS by 4 and 0.3 VP corresponds to IDSS by 2. Okay, the answer is given here 1.2, 2 and 2.4. 1.2, 2 and 2.4. Opposite, fine. Let me wait for some more answers. For VP equals, sorry, for 0.3 VP, that is 1.2 volts, correspond to 1.2 volts, it will be 4 milliampere. And for 0.5 VP, that is for minus 2 volts, corresponding IDSS will be 2 milliampere and 4 milliampere. Okay, for VGS equals 0.3 VP, ID is around 3.9 milliampere. Okay, 3.9, you can take it as 4 milliampere as IDSS by 2. And for 0.5 VP, for 2 volts, it is IDSS by 4, that is 2 milliampere. So we have got 2 points now. One is minus 4 and 0. Then it is minus 2 and 2. And then it is minus 1.2 and 4. Then finally it is 0 and 8. That way we get 4 points. Using these 4 points, we can plot the transfer curve. We can find out VG is R2 into VDD divided by R1 plus R2. Substitute all these values here. You will get VG equals 1.82 volts. Now that is fixed. Now when we get VG equals 1.82 volts, VGS you can find out by substituting this value, VG minus IDRS, 1.82 minus ID into 1.5 kilo ohms. Now we have the transfer curve. We will have to plot that line which is crossing the transfer curve. For crossing it, what we can do is, once we can substitute ID equals 0, next we can substitute VGS equals 0. Now once we substitute ID equals 0, VGS will be corresponding to 1.82. So we have a point that is 1.82 and 0. 1.82 in the x-axis and 0 ID in the y-axis. Next is, let us substitute VGS equals 0. When you substitute VGS equals 0, then ID equals 1.82 divided by 1.5k. Whatever value we get for that, that is going to be 0 and the value of ID. Using these 2 points, we can plot that straight line. So when ID equals 0 milliampere, VGS is 1.82 volts. When VGS equals 0 volts, ID equals 1.82 divided by 1.5 kilo ohms, that is 1.2 milliampere. Now we have correspondingly 2 points, that is 1.82 and 0, then 0 and 1.21. Using these 2 values, we can plot the straight line on the transfer curve. You can see this. We have this transfer curve and we have plotted the straight line using these 2 points. And the straight line we extend this way. When we extend the straight line this way, it is cutting the transfer curve here. When it is cutting the transfer curve here, correspondingly we get IDQ equals 2.4 milliampere and VGSQ equals minus 1.8 volts. So we have got VGSQ is minus 1.8 volts and IDQ we have got 2.4 milliampere. Now I will go back to the previous circuit diagram. I want you students to tell me the answers for VD, VS, VDS and VGD. I will go back to this circuit. Now you tell me the values of VD, VS, VDS and VGD. Note down this value. Note down the value. IDQ is 2.4 milliampere and VGSQ is 1.8 volts. Note down this value. Okay. VGSQ is 1.8, IDQ is 2.4 milliampere. Now I will go back to the circuit diagram. You tell me the values for VD, VS, VDS and VGD. I have written the IDQ value here 2.4 milliampere. VSC is 3.6 ampere. No, it should be 3.6 volts. It is voltage, so it should be 3.6 volts.
Sir, VD is 10.24 volts.
VD is 10.24 volts. Okay, let us verify later. One answer VD is 10.24 volts. One answer VS is 3.6 volts. What about VDS and VGD?
VS is 3.6 volts.
Yeah, that is correct. Even Sayan has given the same answer. Okay, VD is 10.24 volts. Sayan has given that answer. Now, tell me the answer for VDS and VGD.
VDS is 6.64 volts.
Okay. Okay, let me proceed now without wasting much time. I will tell you the answer for VGD. VDS is 6.64 volts. That is correct. Now, from the graph, we have IDQ equals 2.4 milliampere, VGSQ equals minus 1.8 volts. we will apply this value Vd equals Vdd minus IDRD, we get around 10.24 volts. That is the value given by you also, that is correct. Then Vs is ID into Rs is 3.6 volts, that value is also correct. Now Vds is Vdd minus ID into Rd plus Rs, that is 6.64 volts, that value is also correct. Now lastly VGD. VGD is Vg minus Vd. Just like Vds is Vd minus Vs. You can verify this also. Vd minus Vs, 10.24 minus 3.6. You will get around 6.64 volts only, approximately. Here we have substituted using the expression. Otherwise also you can always find out Vds when you know Vd and Vs together, because these are the voltages with respect to ground itself. Similarly, Vg we know that is 1.82 volts, Vd we know that is 10.24 volts. So Vgd is Vg minus Vd. Vg is with respect to ground and Vd is also with respect to ground. We get the value as minus 8.42 volts. Now what does this mean? When we get VGD as minus 8.42 volts, what does it mean? It means that if the transistor has to be in the middle of the transfer curve, then the gate to drain junction or region has to be reverse biased. Just like in BJT also we had this, right? In BJT we used to compute the value of VBC, base to collector. And base to collector junction we used to get always a negative voltage, which meant that the transistor was operating in the middle of the load line. In the same way here the JFET is going to work in the middle of the transfer curve. So naturally we should get VGD as negative. That is the idea here. Now to come to the summary of these three circuits, I have a tabular column here where you can see we are comparing all the three. The biasic type, if it is fixed bias, we have two power supplies there. We should individually have a power supply for the gate and individually have a power supply for the drain. Now in case of self bias, it is single VDD, means we are not going to have a power supply for the gate. We will be using only a additional resistor at the gate. Even in voltage divider bias, there also it is single VDD only. Now the value for VGS in case of fixed bias is minus VGG, because we used a separate power supply for the gate and source was grounded. Now the value for VGS in case of self bias is minus ID into RS, because there was no gate bias as such. Whatever was the voltage across the source resistance, that itself was appearing in a negative way across gate to source. Source was connected to the resistance there. So here for the self bias, the line is minus ID into RS. Whereas in case of voltage divider bias, we have those two resistors and we have a distinct DC voltage given from the power supply itself at the gate. So we have this expression for the voltage divider bias line, that is VG minus ID into RS. So in the case of a fixed bias, the line of VGS is a vertical line, it is parallel to y-axis. Whereas in case of a self bias, it is a slant line, but the slant line is passing through the origin. Why? Because when ID is 0, VGS also becomes 0. So it is passing through the origin 0, 0. But in case of voltage divider bias or VDB, the slant line does not pass through the origin. Why? Because when ID is 0, VGS will be VG. VGS will not be 0. So this line will not pass through the origin. That is why in the case of voltage divider bias, once we have to substitute ID equals 0, next we have to substitute VGS equals 0. Correspondingly, we will get those 2 points. Those 2 points we have to join, and that line when we extend, it will cut the transfer curve and we will obtain the Q point. This way, we have studied these three biasing circuits in JFET. Now, all these three are common source, means with respect to source, we apply input at the gate and we take output at the drain. It is basically common source, and this is in comparison with the common emitter configuration in the case of BJT. Now let us study one more circuit of JFET which is of the other configuration. Let us study the common gate configuration. Till now we studied the common source configuration. Now let us study the common gate configuration. Common gate means gate will be common and we can apply input at the drain and obtain at the source, or we can apply input at the source and obtain at the drain. It doesn't matter much there. As I had told you, in case of VJT, we go for a common base configuration. When we go for a common base configuration, we can either use emitter as input or we can either use collector as input. It doesn't matter much because we are keeping the transistor in the middle of the load line, and then we are going to apply a small signal, and as far as the AC signal is concerned, it is simply moving from collector to emitter or emitter to collector, because AC is always bidirectional. If there is an arrow in the transistor symbol for VJT, it only indicates the DC current flow. AC can flow in both directions. Same way even in case of JFET, whether we give it a drain or whether we get a source, it does not matter where we give the input and where we take the output. Only thing is gate remains common. Let us see the common gate configuration. Now this is that common gate configuration where you need two power supplies now. Recall the circuit which we used in BJT. There also we had two power supplies, exclusive between base and emitter, exclusively between base and collector. In the same fashion, here also we will have a power supply exclusively towards the gate and drain and exclusively toward the gate and source. That is why it is mentioned here as VDD and VSS. And we will have two resistors here, one for the biasing of the drain to gate loop and one for the biasing of the source to gate loop, because gate is going to be grounded. You can simply visualize one power supply here and you can visualize the ground here. Similarly, you can visualize one power supply here and you can visualize the ground here. Anyhow, between drain and source, it is the current is going to flow. Electrons are going to move from source to drain, and the conventional current direction is from drain to source. So here, what should be the polarity of VDD and what should be the polarity of VSS now? Now VSS cannot be larger than VDD. If VSS is larger than VDD, then from drain to source, current will not flow. It is natural, right? VDD has to be larger than VSS here. Only then what happens is, from the power supply, when VDD is larger, current will flow through this direction. If VSS is larger, current will not flow from drain to source. That is the first observation. Okay. Now the second observation is, you may ask, why we need VSS? Why can't we connect the source to ground or this RS to ground, right? If we connect this RS to ground, then we cannot say it is completely common gate. Gate has to be at ground potential. Source cannot be at ground potential. Okay, even though there is no gate current here, source cannot be at ground potential as such. So this VSS also cannot be at zero potential. Now what we do is, you can see here, we can apply input at the source and we can take output at the drain. That is also possible. Otherwise, drain and source are always interchangeable, right? So we can apply the other way also. It does not matter much. Even when the drain and source are non-interchangeable also, AC is going to flow in both the directions. So it does not matter much. So this is the common gate configuration. Let us try to have a DC analysis for the common gate configuration now. In this configuration, the gate terminal is grounded, and typically the input signal is applied to the source terminal and the output signal is obtained at the drain terminal. We have specifically mentioned typically because it need not be mandatory that way. Applying KVL, we can apply KVL separately to the source and gate loop. Now here it is shown VSS is negative. I have been telling you that VSS cannot be larger than VDD. Now if VSS is used in the negative potential, it is still better. That is what we had done in the case of VJT as well. Please recall that the two power supplies at the emitter side and the collector side were not of the same polarity. Same way here, VSS can be negative now. VDD has to be positive now. So when VSS is negative, when we apply KVL, what is this now? Gate is at ground. Now there is a voltage across gate and source. Then there is a voltage across RS. Then there is this VSS. So we can simply write VGS. We can simply write VGS plus ID into RS minus VSS equals 0. Is it so? Am I correct? Am I wrong? Is it minus? If I take this as plus to minus, is it minus to plus? So I'll have to use that particular sign that way. So we can always write as VGS plus ID into RS equals VSS, because the total potential across the loop is VSS. So we can write the other way also, minus VGS minus ISRS plus VSS equals 0. Everything is the same. Yesterday I told you, Aliyalla Magalganda. Just like not son-in-law, it is my daughter's husband. Both are same. You can write it either way. Some textbooks use plus to minus as positive. Some textbooks use minus to plus as positive. But the net result is the same. For example, in the European and Asian side, we have a right-hand drive cars. Whereas in the American side, they have a left-hand drive cars. Only the convention or the usage is different. But the purpose is the same. The purpose is to travel on the road. Same way here. So here VGS equals VSS minus ISRS. Now we know that IS equals ID. So VGS equals VSS minus ID into RS. This way we can apply this KVL to the input loop and we have this particular expression. Now next thing is applying the condition for ID equals 0 milliampere in the upper expression. What do we get? We get when ID equals 0 milliampere, we get VGS equals VSS. We get VGS equals VSS for ID equals 0 milliampere. Why are we computing this VGS? You already know that when we have to go for a graphical analysis, we require all these values. So that is why VGS equals VSS when ID equals 0. Conversely, you can put VGS equals 0 also here. Then you can get the value of ID also as such. But can VGS be 0 in this case? Can VGS be 0 in this case? It depends on the value of VSS which we are using here. So applying the condition VGS equals 0, then we get ID equals VSS by RS using the same expression. ID equals VSS by RS correspond to VGS equals 0 volts. By using these two expressions, we can solve for the quiescent point. So now look at this. We have this transfer curve and we have the values of VGS and ID corresponding in this way. For example, this is now VGS and 0 and this is now 0 and VSS by RS. One is, the first one, see, when ID is 0, we have VGS equals VSS. When ID is 0, we have VGS equals VSS. That is this particular point. Then when VGS is 0, we have ID equals VSS by RS. When VGS is 0, we have ID equals VSS by RS. Sorry, I showed you the other point. This is that point, ID equals VSS by RS. When VGS is 0. And then when ID is 0, when ID is 0, we have VGS equals VSS. When we have these 2 points, we can join this point and then we can find out the point at which transfer curve is being there is an intersection and that particular point corresponds to the Q point. This is similar to the voltage divider by a circuit's functionality. This way we can solve even the common gate configuration. So now let me come back to the slide. Let us apply KVL at the other side now. Let us apply KVL to the whole loop now. We had done this even in case of BJT. VDD minus IDRD minus VDS minus ISRS plus VSS equals 0 if you go in this direction. Now using this expression, as ID and IS are same, we can obtain the value of VDS. So we can write it this way: VDD plus VSS minus VDS into ID into RD plus RS equals 0, or VDS equals VDD plus VSS minus ID into RD plus RS. We can always find VD is VDD minus ID RD. The voltage at the drain is nothing but total voltage VDD minus the drop across this RD. VSC is nothing but minus VSS plus ID into RS, because that source supply is in the other direction. Using all these expressions, we can obtain the Q point also. We can obtain the voltages, different voltages at different nodes of the common gate circuit. So the WebEx is already showing me the time. So let us solve an exercise in the next class for the common gate configuration. See you in the next class. Until then,